In this video, I want to talk about step T induction. In the previous video, we just called it mathematical induction, but we can think of it as step 1 induction. This is a little bit of a generalization. And the idea for this is rather than doing one base case and then the inductive case going from k to k plus 1, we do T base cases where T is some number, some natural number, and we go from k to k plus t. So that's kind of the difference. We'll talk about this a little more precisely in a second. Let's take a look at this example just to see what's going on here. So we want to show that if we have a value n that's greater than or equal to 8, then there exists two whole numbers, a and b, such that we can write n as some whole number multiples of 3 and 5. So you can imagine if we wanted to do an inductive step, I'll just do it over here a little bit. So inductive step, we would assume that there was a k, and this is very loose. We'll write this correctly in a few minutes. But there is a k where we can find an a and a b, so that k equals 3a plus 5b. And you could think, well, it would be quite hard to use this to show that k plus 1 can be written as a whole number multiple of 3 and 5 using this fact. But it would be really easy to show that 3 more than k could, because you just add another 3. So we could show, in fact, it'd be very easy, that we can write k plus 3 as 3 times some whole number plus 5 times some other whole number. And in fact, all we're going to do to show that is we're going to add 3 to both sides. That's really easy. That's really our inductive step here, if we're doing it for k plus 3. So k plus 3 is, well, we have a plus 1 3's now, and we still have b5's, so it's kind of the same thing. Now that we have this, well, let's kind of see what our machine does. I'll draw a little number line here. Here's our little number line. We're going to start at 8, and let me put some ticks here. And they're just whole number or integer ticks, so this will be 9, 10, 11, etc. What our machine says is that, well, if we know it's true for some value, let's say we can prove that it's true for 8, we can use our machine to show it's true for 3 more than 8. So there it is there. So we get 11, and if we know it's true for 11, we can put that back into our machine to show it's true for 14, 17, etc. We can keep going. But we're missing all of these values here, 9, 10, 12, 13, etc. But if we think about it, if we can show it's true for 9, then we can separately plug that base case into our machine, and we get 12, 15, 18, etc. And similarly, we can do a base case for 10. We can just fill in those missing gaps with extra base cases. We fill in 10. Our machine allows us to show the truth of 13, 16, 19, etc. And if we look here, we've done it. Using these 3 base cases now, we're able to prove the truth of our statement for all numbers greater than or equal to 8. And basically, what we're thinking is, hey, if we can find a way to do it for 8, to do it for 11, you just add a 3. If you can find a way to do it for 11, to do it for 14, you just add a 3, etc. Same thing holds for 9. If we know how to do it for 9, to do it for 12, we just add a 3. That's what our result for our induction machine is saying. So, let's talk about what this is precisely then. So, in step T induction, we have some sort of open sentence that we want to prove, and we're going to do it in step T induction. That's the gap between the input and output of our machine, so there's 3 between them. It's a step 3 induction. So what we need to do is we need to show T base cases are true. So we start with the least element, M, and we do in total T base cases, so everything from M all the way up to M plus T minus 1. That gives us T different base cases. And then using this idea, we can show that a result is true for all values in our domain using an inductive case here. So we're going to assume that the result is true for K and show that it must be true for K plus T, whatever T is. What we've done here is a step 3 induction. Okay, so let's do this precisely. Let's write this up. So proof, and this is by step 3 induction. All right, so our base cases. We need n equals 8, n equals 9, and n equals 10. So can we find whole number multiples of 3 and 5, so an a and a b that are whole numbers, so that we know that we can write 8 as some number of 3's plus some number of 5's? Well, this one is pretty easy. We just need to let a equal 1 and b equal 1. Then 3 times 1 plus 5 times 1 is indeed 8. And as a little mini exercise, I'm sure most of you guys can see this. How do we do it for 9 and 10? Well, for 9, well, we know 3 3's are 9, so let's just take 3 a's, let a equal 3, and let b equal 0. Then 3 times 3 plus 5 times 0 is 9. So we have it for 8. We have it for 9. And for 10, well, 2 5's are 10, so we'll take no 3's, and we'll take 2 5's. So 3 times 0 plus 5 times 2 equals 10. So we know how to do it for the 3 base cases. Now we just need to prove it for all other values using our induction machine. So let's invent that. Let's do our inductive case. So we're going to assume that for some K in our domain set, so remember we're looking at values greater than or equal to 8, so it's going to be the integers greater than or equal to 8 that we can find. There are some whole numbers a and b such that we can write K as A3's and B5's. Let me scroll down here. And again, this is just redoing what we've already talked about, but let's write it up good. So we need to show that we can write K plus 3 as 3 times some whole number plus 5 times another whole number. Okay. So let's consider k plus 3. Well, we know k is 3a plus 5b. That's our k there. And we have this plus 3. And so here's a3's, here's 1, 3. Let's combine our like terms. We have a plus 1 3's, and we still have our b 5's. So all it's basically saying is, if we know it's true for one value, let's say it's true, for example, for 14, to show it's true for the value 3 more than 14, so 17, just add a 3. That's all we're doing. And so now we have a plus 1 3's, and we still have the same number of 5's. And let's tell people that these guys are still whole numbers. So since a plus 1 and b are indeed whole numbers, so natural numbers including 0, then the result is proved. And we're done. So remember with the step T induction, if you have a problem and you think an induction might be appropriate, you don't just need to prove it for k plus 1, assuming it for k. If you can prove it for k plus some other natural number, then you can use the step T induction. So this is great for problems where induction is appropriate. And you can easily see, or sometimes not so easily, maybe I'll put a question mark by easily see a way to prove k plus t is true, assuming k is true. And again, let me talk about how I would note that this is an appropriate technique for the problem above. Looking at this example, I know that I have multiples of 3 and multiples of 5. So I know I can still obtain a multiple of 3 by adding 3 to both sides. So I could collect that just like we did here, and I would still have something that's a multiple of 3. So whenever you have multiples of some natural number, maybe a step that natural number induction would be appropriate. If we wanted to, we could have done a step 5 induction as well. So we could have proved the result is true in base cases for 8, 9, 10, 11, and 12. And then rather than adding 3 to both sides in our inductive step, we added 5 to both sides in our inductive step, and it still would have proved both ways are, in this case, equally as good as each other. The first way, the way that we wrote up, is a little bit shorter, so maybe that is slightly better, but they both prove the result in the end anyway, so both are totally valid. And that is step T induction. In the next video, we're going to talk about a last type of induction where rather than assuming that our inductive step is true for one particular value, we're going to assume that it's true for that one particular value and everything below it. And that's a very powerful type of induction. We call it a strong induction.